Everyone, Martin Kaintas and Apostolos Kalovanis, they are going to speak about reliable and limitless off-chain transactions with state channels, demo journey. Thank you.
Hello from my side, I'm Apostolos, and me and Martin, we developed the state channel demo. So let's talk a little bit about the known blockchain challenge, the on-chain challenge. Basically, when a blockchain has more features, it attracts more users. That results in more transactions being executed, which raises the total cost paid. And one way to provide a solution to this problem are off-chain transactions. And off-chain transactions basically move the execution of those transactions off-chain in another way, and then they move the result back to the blockchain. And that provides an increase in both speed and privacy. It's not showing. Is okay. Yeah.
Happens also before, maybe
No.
the kind of presentation.
Should I remove it and put it back in?
Try, but
I will back.
maybe the full screen mode. I don't know.
No longer full screen. What?
Possible?
Now it's full screen again. So do we do it that way? Is it shown
Can
right
you
now?
enlarge this?
Nice question.
I don't know.
Okay.
Maybe
Is it visible now? Great. So no worries. So let's repeat once again what off-chain transactions are. Basically, we move the execution of those transactions away from the blockchain. That means that the consumed energy is not made by the miners, and that way we have an increase in both speed and privacy. And this is where we have the state channels. And what exactly are Æternity state channels? So it is a two-way communication between two parties. This is where they can make multiple spend transactions, exchange messages, and also execute smart contracts with an increased speed and without paying any fees. Let's see a real-life example of what that communication would look like. So let's say we have Bob and Alice visits the on-chain pub. So in this case, let's say that Alice can only pay with card, and there's in this case there's like a bank fee per transaction. And let's say that Alice buys 3 beers. In this case, she will receive 3 receipts and pay. There's going to be 3 transaction fees for each beer bought. Now, if we see again the example in the off-chain pub, which basically translates in real life with the opening a tab. So let's say Bob opens Alice a tab where she buys 3 beers again, but only gets 1 receipt, which has all the details there. In this case, there is only 1 transaction fee paid. And now, if we see this example once again, but with state channels this time, this is where we get a little bit complex. So let's say that both Bob and Alice, through their smartphones, they have their own deployed nodes. Through their smartphones, they connect to their nodes with a WebSocket connection. And they have also agreed on what the configuration of the channel is going to be. For example, they're going to be that, okay, we're going to fund that channel with 100 coins each. In this case, after they have agreed on the configuration, Bob, which has the role of the initiator, is going to create an on-chain transaction which basically creates the channel. By the time that's done, they're both nodes are notified and they communicate through the noise protocol. And now they can execute off-chain transactions. As we can see, the current channel state has 100 coins for each participant. And now, if we go back to beer's example, once again, Alice wants to buy a beer. And in this case, Bob says that, okay, we need to update the current state of the channel. He executes an off-chain update where it says that Alice gives Bob 5 coins. That transaction is communicated through the noise protocol. Alice checks it, she approves it, that yes, I actually want to give the 5 coins to Bob, and she receives the beer. Now, let's say that Alice was feeling tipsy and bought a bunch of beers and a burger as well. And now she's done and she wants to leave. She executes a channel mutual close, which is also an on-chain transaction. He's notified, Bob is notified that, okay, it's time for us to close the channel. He approves it, and right now the channel state is updated with a new balance with half the fee paid for each participant. And by the time the channel closes, it returns its balance back to its user. So now I'm going to hand over to Martin, where he's going to present our demo.
Hello from my side. I'm Martin, and I will show you our implementation of the state channels demo. Our application consists of 3 parts. Basically, our smart contract, which contains the game rules, our bot app, which is a server written in Node.js, which acts as the initiator, and this app basically requests the funds from the faucet. It creates bots for each connection, and also needs to deploy the contract in each channel. Last, we have the user app, which is written in Vue.js and acts as the responder for the channel. And it creates a new account every time the user visits the page and requests the configuration from the server app. Screen problem, okay.
Did you alt-tab? Okay.
No, but I was about to.
Let's escape this. Should I? Let's try this.
No.
Yeah, kind of.
Okay, so now we will show you a quick demo of the app running. Here you can see the starting screen. Let's play. So once you start the game, the accounts are funded, and once that's done, we are opening the channels and deploying the contract and compiling it on each side. I don't know if you saw that, but the user was able to make his selection, and afterwards the bot makes his selection, and once the bot makes his selection, you can reveal the outcome. As you can see, the user lost the first round, and you can play again. And yeah, once we're done playing, we can close the channel, and the balances are distributed according to the outcome. And once the channel is closed, we get some statistics, and here we can also see the more specifically the transactions that happened in the previous rounds. And that's it for the demo. Can you see the screen? Yeah. So let's have a closer look. At first, the client app creates an account and requests from the server to fund its accounts through the faucet. Once that's done and both accounts are funded, we initialize the channels on both sides. And once that's done, the backend deploys the contract in the channel, and the user is notified and also builds the contract on his side. Once both contracts are deployed, are compiled, we can make our selection as the user, and then the user selects, and then the user reveals his selection because it needs to be hashed so that the bot cannot cheat. And we also get the outcome. So in more detail, as you can see, all transactions need to be signed by both parties. So here we have the user hashing his selection as the first action for each round. He proposes this transaction, and the bot then has to confirm it. Once the bot confirms the transaction, it selects, in this example, it selected rock, and it also signs this transaction and sends it to the user through the channel, who needs to co-sign it. Yeah. After this, the client app will reveal his selection and sign the transaction, and the bot will also need to co-sign this transaction. The last step is to close the channel, and this happens when we click on End Game. We will sign a channel mutual close transaction and send it to the channel, to the bot, which will accept it and close the channel. Once the channel is shut down, we can see the statistics. Yeah. So what if someone tries to cheat? Well, let's say state channels provide dispute mechanisms, and in the event of so basically, if a malicious user tries to, basically, if the parties are in disagreement, they can basically use the blockchain as an arbiter and call the contract on chain, and this will then update the next off-chain state of the channel. Using the force progress transaction. Using the snapshot solo transaction, users can basically post the off-chain state on chain, and basically, even if one party goes offline, we can say that there is a recent state on chain, and the channel cannot be closed using an older state, and cheat in this way. And lastly, with using this last TX, if a malicious party tries to cheat in some way, for example, force progressing with an invalid state or an older state, the other party can basically dispute that with a /TX and provide a newer state that is accepted by both parties and has a bigger round index. So that's it from our side. If you have any questions.
Questions?